Okay, we're getting back after break here. So, one of the last things that we're going to check out in the post is how to enable tilted work planes. This is also known as G68.2. So I suppose we should add that to the document. And this is a little cheat sheet document. Okay. So this is a little cheat sheet document that one of the guys had put together when I was working back at CNC Software. And it was basically a little quick how to implement G68.2. And there are some little things that I've discovered over the years, and I've also implemented some different logic to do the calculations for G68.2 because some machines have different implementations. In other words, how do they list the rotations, and in what order do we perform the rotations? So what is the G68.2 in general? Let's see if I've got... something that will help explain this. So, is this in the Dropbox folder? No. I don't see any reason I couldn't put it in the Dropbox. I believe all this stuff is available directly from Fanuc. I got it from Fanuc AE, and he didn't tell me that I couldn't distribute it. So, I mean, I'm not going to give all the manuals that I've got away, but I don't see any reason we couldn't do this one. I think, you know, in general, anybody that would be interested in it in my class, it's because they want to implement G68.2 in a post, not the Fanuc, the G60. Oh yeah, absolutely. Yeah, I'm actually going to put both in there. So I'm going to do this document and the Word document as well. They're not in there currently, so don't go looking for them just yet. But I'll put them in there. So this doc's also nice because it's got, for Fanuc, basically all of the different 5-axis advanced functions that you might encounter on their, you know, because Fanuc makes the hardware that controls the drive motors. They don't build the machines, right? So they build the control, they build the software, they build the hardware boards and things like that for driving the motors. But the logic is implemented based on the G codes. So things like tool center point control, which is really dynamic tool length compensation for 5-axis machining. That's all tool center point control is. As far as what it does on the machine, it also makes the tool tip stand still and the machine move around the tip of the tool when you're doing rotations. So there's a lot of good stuff in here. Tool center point control, 5-axis cutter comp, NURBS machining, nano smoothing, tilted work planes, WSEC, which is the workpiece setting error compensation, and then some other stuff. And the other cool thing is it tells you the parameters on the control that affect these modes. So what is tilted working plane? For those of you guys that have Trunnion style machines, you are spoiled. And you are spoiled because the tool on your machine is always aligned to the Z-axis of the machine. And that means that in general, when you're doing work on an angled face, your machine is going to rotate the table to present the face to the spindle. And all of your normal can drilling cycles, cutter compensation, and that kind of stuff is all available to you. On a gantry style machine, a head, where the tool pivots around what is generally a stationary workpiece. I mean, you may have X on the table, but in general with the gantry, the tool is moving around the part. And when that happens, now all of a sudden when that tool is angled, you can no longer use can cycles or cutter compensation without using a function like tilted working plane. And what tilted working plane does is it takes the coordinate system of your workpiece location and it mathematically rotates that coordinate system. That's the rotation portion. And it can also optionally do a transformation. In other words, moving from your workpiece origin here over to, say, a point at the corner of this feature. A lot of the times we tend to move that origin because it then makes it easier to measure or gauge either the feature or the datum on the workpiece. So we can move it to this corner over here, and now maybe we're going to take our probe out and touch off the side of that workpiece so we know that we're exactly where we think we are. And now that the coordinate system is aligned to this angled face, we can now use can cycles. So we can do can cycle drilling as if this face was now aligned to our Z-axis. It also means we can reference this face as 0. So when we look at our can cycle, if you see, minus 1.25, and the origin of your plane here is on the face, you're going 1.25 inches deep. Otherwise, if we leave the origin of this plane back where our work offset origin is, when we read the can cycle, it might be minus 2.8493, and it's, it makes it really hard to not only, read the code, but it makes it virtually impossible to adjust at the machine. I mean, yeah, you can do it, you can trig it out, but most of the time, if you also move the origin, it just makes life easier. So the G68.2 command causes the programming coordinate system to switch to the feature coordinate system. The commands in all subsequent blocks are assumed to be specified in the feature coordinate system until G69 appears. If G68.2 specifies the relationship between the feature coordinate system and the workpiece coordinate system, G53.1 automatically specifies the positive or plus Z direction of the feature coordinate system as the tool axis direction, even if no angle is specified for the rotary axis. For explanations about the tool axis direction, see figure 1.2. So this is the tool axis direction command, and most of the time when you see G68.2 used, you're going to see G68.2 G53.1 right after it. G53.1 will cause motion if your tool is not already positioned to be lined up to this orientation. If you have in your post told it to automatically rotate and move to position before you call out the G68.2, then G53.1 causes no motion. So be aware of that. If you've already positioned, you'll get no motion. If you haven't positioned, what it does is it says, okay, here's how I'm positioned prior to the call. Now I call my G53.1, and all of a sudden I'm going to rotate my, my head so that the tool axis is now aligned to the z-axis of my feature coordinate system. So, with G68.2, we have an XYZ position, which tells us the location of that 0 point on the feature. So relative to wherever the original coordinate system was. So basically it's an offset distance from where, say for example, we're using G54, like they show here. So that XYZ after the G68.2 is the offset distance from our active workpiece coordinate. Could be 54, G54, could be G55, could be G56. It's whatever is active at the moment, and the offset is relative to whatever is active. Many times we'll use G68.2 without moving the 0 point. But keep in mind, if we do that and we're, working on this feature over here, the depth calculation for these features just got harder. So there is an advantage to moving the XYZ position as well. There are different ways to set up and interpret the G68.2. So here they show using roll, pitch, and yaw angles. So X would be the roll, Y is going to be the pitch, and then 3 or Z is going to be the yaw. And there is an option with this Q value to change the way that the calculation is done. That's what makes implementing this sometimes, what is G69? Yeah, G69 cancels the tilted work plane command. The fact that we can do rotation different ways, whether we're calculating X first or Y first or Z first, the problem is, unless you really know the machine really well, a lot of people don't know these options are available, so they try to use G68.2 and it just doesn't work on the machine because they don't know which order the machine's expecting. So the angles are given as IJK. You're going to see, G68.2, sometimes P1. Here they're showing Q values as well. So you might say G68.2 P1 Q 132 means we're going to rotate X, then Z, then Y. A very popular one that they do is it's like ZXZ. I don't think I see it here. Yeah. So because this is still roll, pitch, yaw. There's a different option with P2. This is using 3 points. So you define 3 points out in space. I've honestly never done an implementation with the P2 option. Sounds like a real pain in the ass, but certainly possible. There's an option for doing it based off of 2 vectors. There's an option for projection angles. Okay. So they also give some examples down at the bottom. Canceling it on milling machines, it's a G69 to cancel. On turning machines, it's a G69.1. Husker says G68.3 is handy when hand coding something quick at the machine. Nice. Yeah. So yours is a ZXZ. So the IJK values, it's going to be a rotation about Z, a rotation about X, and then a rotation about the Z of the rotated plane, which you need to know which rotations to apply in which order in order to get the mathematics right. There is the tool axis direction. Bum, bum, bum. Okay, well, we're going to do the one, we're just going to do the standard implementation like they show, and you may need to work on different logic for yours, but at least you'll know the places to go and make the modifications. Then working out the logic is a simple matter of, finding out what kind of equation you want to use, creating some variables that act as the variables in the equation, and putting your brackets in the right place. One of the things that that kind of amuses me about some of these really complicated functions, when you break it down, there's only 4 operations. I mean, it's addition, subtraction, division, multiplication. Yeah, you've got things like powers, but really that's powers is really just multiplication taken to another level, and square roots, same kind of thing. It's division, right? It's like division and multiplication mixed. So let's look at how we implement this in the post. So the first thing we do is we turn on top map. So up near the top of the post, when we get into the 5-axis settings, we have machine type. And then as we come down, there it is. It's in the output formatting. Top map. Output tool plane toolpaths mapped to top view. The post must have code added for your machine control. So we say 1 to turn on top map. Modify the rotary axis settings in the post block P Nutate Restore so that they match with the initial rotary settings right above this post block. So we go find P Nutate Restore, and we make sure that our settings here for rot axis 1 and rotdir 1, vec y, negative vec x, vec y, negative vec x. An example for one of our programs with no actual tilted work plane used. I-90, K270. Spins 90 degrees about Z, 0 about X, and then another 270 about Z. Yeah, so there you go. So the other problem is when we start talking about the way that the rotations happen, there's always basically two pairs of angles. I shouldn't say that, because on your machine you've got a more limited travel range. But in general, on a trunnion, there are two pairs of angles that should get us to the same spot. And so we've got to figure out on your machine what series of numbers in the correct order will actually make it rotate. So yeah, you're saying it spins Z on X, and the X spins on the new Z created by the first spins. Yeah. Am I using a Matsura machine? Right now we're doing the Doosan, the DNM 350. So this is the one that we're working on with Mike. I'm sure the implementation for yours, Wing, would be pretty similar. We'll need to know, what the rotation value is, the way that your machine has the implementation done. But other than that, it should be pretty similar. Okay, VecZ rotates towards negative vec y. And the point here is that whatever settings were the correct settings here need to be matched down here. Is that a head machine for the K output? In general, the G68.2 can be set up to work for either a head or for a table style machine. The one we're implementing right now happens to be a table just because that's the post I'm starting with. All of the controls have the ability to do, G68.2, XYZ, IJK. And IJK, well, I'm and that's fine, Mike. I'm actually responding to Steven. The IJK rotations can be interpreted many different ways. A lot of people think it means just, rotate, about this axis, but it can be interpreted different ways by the control. And that's what we really need to figure out is what formatting does your machine use to rotate the angles. I can show you an example that I did. So this is for a Matsura MX520. And it works by reading the tool plane matrix. So M1 through M9 represent the tool plane matrix, and we import it into a tilted work plane matrix that I created. So it's 9 variables, starting with M1, going into 9 variables, starting with TWP XX. And then we look at the z-axis vector to determine orientation. And if it's less than 1, what this is missing is a bracket. So if it's less than 1, it's going to execute this code in here. Otherwise, it's going to execute that code. And these are the calculations to get the various values we need. In this case, I set it up with theta, phi, and psi as the angles that I wanted to calculate. And let's see, I took theta 1 as the arc cosine of the z-axis, and then did sine theta as the sine of that. Then we used a tan 2 to calculate the other angles. In another case, theta was actually just 180, and so I calculate the psi and the phi values. Otherwise, the first one is 0. I calculate the middle one. The second one is 0. So really, it really depends on the actual machine you've got and how that is supposed to be formatted for that machine. So for our example, let's get this to work. So we set up pnutate restore. Modify the values for the variables ns-axis x, ns-axis y, and ns-axis z if necessary. 5-axis uses the nutating variables. Tool plane based uses the s-axis variables. So we need to determine if there is a shift for your machine mic. Where's the c-axis faceplate in relationship to the a-axis? Did you ever get that figured out? Not exactly. Okay. I'll have to work on a procedure to get that. Let's just say there is a shift. You know what? So let's just say right now there is no shift. We can put one in if we need to. Modify the value for the variable top type. So there are a couple of different options. Depends on the machine. There's this thing called the G7 rotation. These are for some of the older 5-axis machines that have like settings to give you the approximate rotary radius for each of the rotary axis to allow it to help with the feed stuff. But we can either select C-axis is the primary, and a secondary of A with y positive 0, or a secondary of A with y negative, or a C with a secondary B minus x0, a secondary B with a positive x0. Sometimes there is a easy solution with one of these that you say, oh yeah, that's exactly my machine. It's a C-axis, yeah, and we've got an A that rotates on X and, you know, Y positive 0, so that's great. If we go look at what we have here, that's exactly what we've got. Y positive is the 0 direction for the primary, and the secondary is an A. So ta-da, we can just set this to 1. And everything should come out great. The reality is I typically set this to 5, and I use P top type AX and P top type limits to do a custom configuration for the top type. So, if the value of top type is set to be 5, modify the rotary axis settings in the post block P top type AX and P top type limit accordingly. In P top type AX, also check the axis label. Make sure they are set correctly. So we're going to go look for P top type AX. And this is where we do the setup for our G68. So primary is a C. Secondary is an A. If it was a B instead of an A, we would swap str_n_b_axis with strn_a axis. So we would swap those two. In our case, the primary and secondary strings are already set correctly. Now we need to make sure that our vector directions are correct for calculating the angles. And this is just like the setting that we were looking at before, where we changed the result, update global, rot axis 1, rotor 1. So it was positive vec y, I believe it was rotating towards negative vec x, and it was positive vec z rotating towards negative vec y, I want to say, but I gotta check. Yep, rotating towards negative vec y. So we make that a negative vec y. Now, we also set our top map limits. And this is just the same as we set our limits before. So, primary, low and high. Secondary low, 150, high of 30. Primary int, high and low, we're going to leave the same. And we're going to set these to match. So now we're on to step 6. Modify the mapping logic in the post block PG68_map and PG68. Basically, the axis to be rotated around may be modified. In PG68 map, check the axis X variable and make sure it is set to the correct vector to rotate about. In PG68, check IVEC and make sure it is set to the, let's say, correct, just to be clear, to the correct axis vector to rotate about. Also check the variable mapr is set to be the correct angle. The sign of this angle may need to be changed depending on rotary axis type. For example, mapr should be set to P out and S out for a head-head machine. Okay, the G code for G68, G69 may be modified if necessary. So let's go to PG68 map. So PG68 map, if P out or S out. What we're basically doing is calculating the values that we're going to use to calculate all of our map stuff down below in PG68. So rotate X abs back. X abs shift equals vector equate X abs. So we're taking the current X position value and holding it here. Axis X equals vector equate C axis X. What this means is that this vector is a helper variable that holds a rotation vector used with the rotation functions rotate P and rotate V. C axis X is a vector constant. Sorry, I'm reading a question real quick. I am not sure, honestly. The calculations themselves are all going to depend on the implementation of the individual control. So whether or not the same IJK values on the G68 produce the same motion in those two different machines is a total crapshoot. You may get lucky and it may work just fine. But if not, you're going to have to go to these calculations to make the edits. So let's talk about what we're doing here. Axis X is part of three variables: axis X, axis Y, and axis C. And they are the vector components of a rotation vector. That rotation vector is typically 1 unit long and is either aligned on the x-axis, y-axis, or z-axis. C-axis X tells me that axis X here is now being set to be vertical. That's what the C-axis X does. So then we take our point, and it says x abs underscore s equals rotate vector, and we're actually rotating this point using the primary vector rotary angle that is calculated in the PSB. So when we do this, this value is already calculated for us in the PSB, and we just have to make sure that we are rotating about the correct vector direction. in this case, we do the primary and then we do the secondary. So the primary is C, but the secondary is not B. The secondary is A. So down here, this should be A axis X instead of B axis X. And this says we're just taking the same point and we're rotating it minus the primary vector rotation. So what this logic does here is to take the position that's in the tool plane, the XYZ position in the tool plane, and rotate it into machine coordinates. And what that allows us to do is to get the offset distance between the two in terms of being back on the machine. Okay, so we make sure this one is correct. And axis X equals rotate vector, primary vector rotate, so we're rotating it the correct direction. Basically, we're taking the vector and we're rotating it along the primary. So that makes sure that this one's in the correct spot. And then X abs S, rotate vector, minus the secondary vector rotate angle, and we're applying it here. The important thing to understand about this logic here is that you'll only need to modify this line and this line. Yeah, that's, you know, Stephen, that's the real answer, is that when it is a post that was bought from somebody, got to make them fix it. The thing that most post writers have a really hard time with, and I struggle with this sometimes myself, is that a lot of users really don't know their machines very well. Some do. And those are really great joys to work with, because they can tell you what needs to be changed and why, and you go and you change it, and you only have to do it once because they give you the correct info the first time. And half the time, you know, as a user, you're picking up a machine that's brand new, or, you know, you guys bought it from some other company on sale or whatever, and now it, you know, didn't show up with any manuals, and you're trying to figure the thing out. And unfortunately, you know, half the time when that situation occurs, they, you know, somebody goes to a post writer and says, hey, I want to post for this machine. Okay, great. What can you tell me about it? Well, it's a 5-axis. Okay, well, how is everything arranged? Well, here, I'll send you a picture, you know, and it's like, trying to get the right info can be like pulling teeth sometimes. Okay, so basically we make sure that the primary is set, in this case vertical as the C axis X, and then we make sure the secondary is set. So, by default, the way that this G68 is set up it is set up to output 2 G68 rotations, which technically you can do. You can do, G68 and rotate about one axis, and then G68 again and rotate another one. Kind of sounds like trying to get some parameter info from some MTBs. Yeah, it can be absolute nightmare sometimes. So this is kind of the very old school way of doing the G68 rotations. Because really what we're doing is a rotation about a single vector with a single angle here for the G68, and then we're doing another one down here to get the secondary. So we're going to redo this so that we get the correct G68.2 rotation. Actually, you know what? Let's see what we get first so I can show you what kind of the default output is. So here, the IVEC value, C-axis, vector equates C-axis X. And down here, we're doing B, and this should be A for the vector direction. So let's see here. If we look at our S map mode, right now it's set up to be G68, which I would expect. Let's check our map X, Y, and Z values. Okay, so they must be taking this right now to basically just be 0, 0, 0, 0, all the way across the board, because there's no logic that actually sets that. So here's yeah, those are variables that are inside the PSB as well. So what they're saying is make sure the IVEC variable is correct for which one you actually want to rotate about. So if we were going to rotate about the C-axis, that would really be the KVEC, because we're going to rotate by whatever this angular value is here with G68. So if we say KVEC here equals the C-axis, so we'll get that as 1. The rest of these will be, so we'll get 0, 0, 1, and then the angle with the KVEC here. And this one is A, which would correspond to the I, so it should be IVEC anyway. So map R is negative, all that. Previous map R. Okay, so those should be correct for the G68 method. Correct vector to rotate about, we did that. Also check map R set to be the correct angle. P out for C-axis. S out, yes. And okay, so map R should be set to P out and S out for a head machine. It may be S out and P out for a table. So for a table, we probably have to rotate the secondary first. So we'll say S out we're going to make this one P out, and we're going to make this A axis X, and we're going to make this I vec, and this one's going to be K vec. So we're going to say primary, and we're going to say secondary. So we're doing the X axis, the A, which is I vec, which is this guy here, and then map R is going to be the secondary. And this, so this should be S out, and okay, so this is primary K vec is going to equal C axis X. If P out, map R equals negative P out. Alright, so that's all set according to what we've got for this document. Code for G68, G69 may be modified if necessary. For some machines it may be G68.1 and G69.1. Add code to turn on spindle for G68 mode in P, go to start tool, and P, go to start end tool. This is to fix a bug in our 5-axis post. Add code to turn on G90 mode in P, go to start tool. This is to fix a bug in our 5-axis post. The post block P, go to start tool, and P, go to start end tool should look similar to below. So P, go to start tool. Let's see if we can get this. Okay, so we got our G tool plane mapping mode. So what we're missing here is and $, we need to force speed, need to force the spindle, and we need to call P gear, which will only output the gear code if it's actually turned on with the use gear switch. Okay, we've got that. We look at our PWCS and we force SG abs inc, which is going to output G90, assuming we are in absolute coordinates, which we typically are at the tool change. Okay, so you can see the changes we made here for spindle on and output the absolute. Under go to start end tool, regular. So here's go to start end tool. Here's my PG68 map, and we need our you notice in this case it's not force. So here we let modality do its job. And if the speed has changed, why do they force XO and YO in the last one? I'm not sure what you mean by last one. You're talking about for the calculations for the G68? We'll have to come. Let me get through this real quick. Okay, we got the go to start end tool. Add code. Ooh. Add code to update the work offset at the end of P go to start tool and P go to start end tool. So let's go to start tool at the very end. We're going to update the work offset. And at the very end of go to start end tool, we're going to update the work offset. The G68 rotation center will always be the WCS origin in our current post. This may need to be fixed if a customer wants the rotation center to be the tool plane origin. Be aware of miscellaneous integer number 6 that would affect the output. The fix needs to be related to the settings of MI6. So you see here in PG68 map, if add work shift equals 0, map x equals vector equate TOX. So work shift is not turned on. Rotate about the tool plane origin. I think it's backwards. I think work shift is turned on when this is 0. And else map x equals 0, map y equals 0, map z equals 0. Work shift is turned off. Yeah, this is backwards. Rotate around WCS origin. So this is how we get the different origins to populate for the G68 rotation. So what we're going to do is fix this first, and then we'll come back to this thing again. And that is on canceling it, PG69, if top map we need to add and previous map mode equals 1. So we find PG69. If top map and previous map mode equals 1. Then we cancel it with the G69. Alright, so we haven't done the origin thing yet, but let's see what this looks like without it. And we know we're getting, shouldn't matter anyway. And if we look, this one's in top, which is why we're just getting regular top mode type stuff. And it's not till we get down. That one's top again. So what we're getting, and you can see it right here, we position to C0 a negative 90, then we call out the coordinate rotation, and we're getting rotation about X. Now again, this is if we're set up for the standard style G68, not G68.2, but G68. where we're doing a single axis of rotation and it's flagged basically as A, B, or C. And we'll have to see if that really does need to be positive or negative 90. So as right now, in the post, we are taking the negative value. So if it really should be the actual value, we'll take out these negatives. And let's repost. All right. So negative 90, we get the negative 90 rotation, and now all this code should be relative to, it's the same origin, but now it's relative to that face that's actually being cut. And G69 to turn it off. Now, one thing that we can also do here in the post, we go back up to force C init, force C initialize. So break move head, force C init is 1. Okay. Oh, good. Okay, so it looks like you can do incremental to wind up past 360. So that's good to know for if you do need to do any kind of simultaneous work. Now the real trick is to find out if there is a real limit. I mean, 3600 degrees is 10 revolutions. Will it do 36,000? You know, that'd be 100 revs. And if it does 100 revs, you know, will it do 1,000 revolutions? I mean, even at rapid, you're going to sit there a while to find out, unless you can get information from the manufacturer where they're like, look, dude, it does, you know, 1,600 revolutions and that's it. Isn't it like a Sudcoma or something you got? Yeah, but you've got isn't it like an aftermarket rotary? Or did it come with the machine? Okay. Okay. All right, so when we look, it's rotating into position, it's calling out the G68, it's doing its cutting. Here's one with 2 rotations. Now it looks like we do have at least one error. So let's go find. Okay. And why? Well, that's funky. So we're going to do those first. Then we're going to do these. All right. And posting with that post. Okay, so we'll put in a little debugging action there. I vector rotation there, that's good. Why aren't we getting K vector rotation here? You should, that'd be awesome, man. You should put like a counter, like make it count up to like 30,000 and then just, you know, put out like, John, you're an ass. Like we're just right in the middle of the, you know, peeling out statement. Now, what would be really fun is if you somehow built like the random number into that equation, so it would just do it totally at random spots. Man, I have no idea why it's doing that. I just don't know. You just got to make it like be something like plausible that like, you know, just some kind of weird random like warning, like, dude, check your vector, Victor, or something, you know, something where they're just like scratching their head. So it appears, at least from what I can see here, that C-axis X is not set to 1 the way that A-axis X is. So is that really the only time we mentioned vector in here? All right, so well, the silly thing about it is it's really just 1 that we're looking for. Yeah, or a movie quote, that'd be great. Okay, so, because really what we want here is just 1. We don't even need freaking vector equate. Okay, so we just set them to 1. Force PG68. I don't know. What I'm really looking at was I wasn't getting a 1 for my K value. So now I'm getting my K1, which is what I wanted. Oh, and I gotta comment out my other comment here. Okay, we are nearing the home stretch, guys. The one other thing I wanted to do was here in PG68 map. If we go look at pmisc int, you'll see that we get add work shift, not work shit, guys, but it's work shift from mi6. Little post humor for you. And the default value for add work shift is always 1 to come from the WCS origin. So when it's 0, so this comment is, so if work shift equals 0, work shift is turned on, rotate around the tool plane origin. So what we're going to do is do, and okay. So if it equals 0, then we want to grab the position map X. We want to grab it from the tool plane origin. So map X equals vector equate TOX $. Else map X equals 0, map Y equals 0, and map Z equals 0. So if we go to this guy. Check TLO. All right. So C minus 90, A minus 90, C 180. So what we're going to do, we're going to go to the planes. A minus 90, C 180. I was hoping we'd have something good on there. That's okay.